Section 13.4 Ways of expressing concentration. The concentration of a solution can be expressed either qualitatively or quantitatively. The terms dilute and concentrated are used to describe a solution qualitatively. A solution with a relatively small concentration of solute is said to be dilute. One with a large concentration is said to be concentrated. We use several different ways to express concentration in quantitative terms, and we examine 4 of these in this section: mass percentage, mole fraction, molarity, and molality. Mass percentage, parts per million, and parts per billion. One of the simplest quantitative expressions of concentration is the mass percentage of a component of a solution, given by mass percent of a component is equal to the mass of the component of a solution divided by the total mass of the solution times 100%. Where we have abbreviated solution as SOLN, percent means per 100. Thus, a solution of hydrochloric acid that's 36% hydrochloric acid by mass contains 36 grams of HCl for each 100 grams of solution. When we express the concentrations of very dilute solution in parts per million or parts per billion, these quantitatives are similar to mass percentages, but use 10 to the 6 a million or 10 to the 9 a billion respectively in place of 100 as a multiplier for the ratio of the mass of solute to the mass of solution. Thus, the parts per million are defined as ppm of a component is the mass of a component of solution divided by the total mass of solution times 1 million or 10 to the 6. A solution whose solute concentration is 1 ppm contains 1 gram of solute for each million grams of solution, equivalently 1 milligram of solute per kilogram of solution. Because of the density of water is 1 gram per milliliter, 1 kilogram of a dilute aqueous solution will have a volume very close to 1 liter. Thus, 1 part per million also corresponds to 1 milligram of solute per liter of aqueous solution. The acceptable maximum concentrations of toxic or carcinogenic substances in the environment are often expressed in parts per million or parts per billion. For example, the maximum allowable concentration of arsenic in drinking water in the United States is 0.010 parts per million. That is 0.01 milligrams of arsenic per liter of water. This concentration corresponds to 10 parts per billion. Mole fraction, molarity, and molality. Concentration expressions are often based on the number of moles of one or more components of a solution. The 3 most commonly used are the mole fraction, molarity, and molality. Recall from section 10.6 that the mole fraction of a component of a solution is given by moles of the component over total moles of all components. The symbol X is commonly used for mole fraction with a subscript to indicate the component of interest. For example, the mole fraction of hydrochloric acid in a hydrochloric acid solution is represented as X sub HCl. Thus, a solution containing 1 mole of hydrochloric acid, 36.5 grams, and 8 moles of water, 144 grams, has a mole fraction of HCl of 1 mole over 1 mole plus 8 moles, or 0.111. Mole fractions have no units because the units in the numerator and the denominator cancel. The sum of the mole fractions of all the components of a solution must equal 1. Thus, in the aqueous HCl solution, 1 minus 0.111 equals 0.889. Mole fractions are very useful when dealing with gases, as we saw in section 10.6, but have limited use when dealing with liquid solutions. Recall from section 4.5 that the molarity of a solute in the solution is defined as moles of the solute over liters of solution. For example, If you dissolve a half a mole of sodium carbonate in enough water to form a quarter of a liter of solution, then the solution has a concentration of 0.5 moles over 0.25 liters equals 2 molar in sodium carbonate. Molarity is especially useful for relating the volume of a solution to the quantity of solute it contains, as we saw in our discussions of titrations. The molality of a solution, denoted lowercase italics m, is a unit that we have not encountered in previous chapters. This concentration unit equals the number of moles of solute per kilogram of solvent. Thus, if you form a solution by mixing 0.2 moles of sodium hydroxide, which is 8 grams, and half a kilogram of water, which is 500 grams, the concentration of the solution is 0.2 moles divided by 0.5 kilograms equals 0.4 molal, that is 0.400 molal in NaOH. The definitions of molarity and molality are similar enough that they can easily be confused. Molarity depends on volume of solution, whereas molality depends on the mass of the solvent. When water is the solvent, the molality and the molarity of dilute solutions are numerically about the same because 1 kilogram of solvent is nearly the same as 1 kilogram of solution, and 1 kilogram of solution has a volume of about 1 liter. The molality of a given solution does not vary with temperature because the masses do not vary with temperature. Molarity, however, changes with temperature because the expansion or contraction of the solution changes its volume. Thus, molality is often the concentration unit of choice when a solution is to be used over a range of temperatures. Conversion of concentration units. Sometimes the concentration of a given solution needs to be known in several different concentration units. It's possible to interconvert concentration units as shown in sample exercises 13, 6, and 7. To interconvert molality and molarity, we need to know the density of the solution. Figure 13.19 outlines the calculation of the molality and molality of a solution from the mass of a solute and the mass of the solvent. The mass of the solution is the sum of the masses of the solvent and solute. The volume of the solution can be calculated from its mass and its density.